Hello, my name is Panina Levine, and I'm a master's student at MIT. And today I'm presenting on behalf of Dr. Farheen Naqvi in my group, and our work uses a technique called NRTA, or neutron resonance transmission analysis, for isotopic identification using an isotopic neutron source. An issue today is that nuclear material does go missing, and the IAEA says that illicit trafficking of nuclear materials poses a threat. Our work aims to combat this. Specifically, between 1993 and 2020, the IAEA reported 12 incidents connected with trafficking or malicious use of highly enriched uranium, 3 of plutonium, and 5 of PUV sources. The big question is, how can we detect special nuclear materials so we can keep track of it and be accountable for where it is going and ending up? And even more specifically, how can we detect concealed special nuclear materials when we can't see into a package or into cargo to see where that material is, and as well where it might be shielded? Our work is relevant to the NNSA mission because we're looking to develop technological advancements to develop compact, mobile, and on-site setups for having isotopic detection and isotopic analysis capabilities. The NNSA aims to prevent state and non-state actors from developing nuclear weapons or acquiring weapons-usable nuclear or radiological materials, equipment, technology, and expertise. And our work aims to do this. Specifically, NRTA is useful for warhead verification in arms control treaties and for fuel enrichment analysis, as well as a number of other applications such as archaeology. It's really useful whenever we have high Z elements that we need to identify the isotopic composition, but we can't see inside or we don't know what is inside that target. NRTA works by using the neutron resonances, which are unique to individual nuclei as a sort of fingerprint for nuclear structure. In the 1 to 10 EV range, as we see here, for plutonium, the various isotopes have different neutron resonances, which act as a fingerprint, and therefore we can use this to identify what that isotope is. A epithermal neutron beam is passed through a target, and then by measuring the attenuated beam and looking at the absorption lines, we can see what that target was. An important feature of this is that in this epithermal 1 to 10 EV range, common shielding materials such as metals and plastics do not have resonances, so you can't fake these materials. Currently, NRTA is only carried out at very expensive beamline facilities such as NIST Center for Neutron Research, where we might need extremely high levels of precision for cross-section measurements, for example. And this is because we haven't developed any facilities for NRTA. Our lab is trying to make NRTA compact and suitable for on-site use via alternative methods of beam generation. And we're looking at this through various ways. Also in our lab, and you can see this work from Ethan Klein, is looking to generate the beam using a DT generator setup. Specifically here, what we're doing is generating the beam using an isotopic neutron source. So in this case, an ambi source. And just for scale, that will reduce the time of flight distance. Like currently in current facilities, we might see 25 meters, but we don't need that level of precision. So our site would have just about a ½ meter time of flight distance to around, a ½ meter to 1 meter or so. Now detailing the kind of how does this system work. We start with our isotopic neutron source, in this case ambi, and the neutrons coming off that source at a rate of 10 to the 4 neutrons per second will interact in our first detector, which is a liquid scintillator, and detects fast neutrons. And this is where our time of flight starts. The neutrons then get moderated in the liquid scintillator and travel across the time of flight distance, pass through a cadmium foil, which removes thermal neutrons, and our target, which is the object we're trying to measure and detect. And finally interact in detector 2, which is a lithium-6 GS20 glass detector, which is where our time of flight ends by detecting thermal neutrons. Through simulation in Grasshopper, which is a JAUNT4 backed simulation engine, we have started by looking at comparing our true energies of the neutrons hitting in detector 2 versus the time of flight reconstructed energy. based on those coincidence measurements. So really, we're looking at coincidences between detector 1 and detector 2. And so what we see here is comparing our true energies versus time of flight reconstructed energy. And ideally, what we would want to see is all of our neutrons along that 1-to-1 correspondence line where we are perfectly reconstructing our actual energies. And in reality, I mean, through simulation, we do see pretty close to that. Obviously, there's going to be a little bit of a range based on moderation time in that liquid scintillator, as well as scattering off of the walls. And what we're comparing here is our real coincidences versus false coincidences, where we might have a scattering or we might have two independent events which happen to produce a coincidence in our window between those two detectors. And here we're comparing two different neutron source rates. So on the left, we have 10 to the 4 neutrons per second, and over here, 10 times higher rate at 10 to the 5 neutrons per second. And you can see as we have higher neutron rates, it does become harder to exclude false coincidences. We do kind of have a pileup of events. Continuing on from that, we want to see how does our source, how well does it show those attenuation lines where the neutron energies get absorbed or scattered. And here we're continuing to compare neutron transmission for two different source activities. Once again, 10 to the 4 neutrons per second and 10 to the 5 neutrons per second. And so for both sources, you can really see those dips. However, we can see that this is better for a lower source rate as we do start to see more false coincidences for the 10 to the 5 faster neutron rate. So source activity of 10 to the 5 neutrons per second increases the false coincident rates, and hence we see more background underneath these dips. But if we can find a way to model this background, then we can potentially use a higher source rate, and that will significantly decrease our measurement time. For example, here, this would be a 10 times faster experiment, which is also really important. So we are looking into ways to minimize that background. Next, we have simulations using a silver target. So we still have cadmium and we still have tungsten, and now we've added silver. And this is for 10 to the 9 simulated particles, once again at a rate of 10 to the 4 neutrons per second. So the slower rate that we were looking at before. And here we can clearly see those attenuation lines, those dips at our resonances. And an important thing to note about this system is that our resolution is dominated by the spread in moderation time. So we actually have a better resolution for our higher energy neutrons. And this is because there's going to be fewer interactions to moderate that energy down in that detector 1, which is the liquid scintillator. And because of that, there's going to be less spread in those moderation times. So for example, with a 1 eV neutron, we have a spread of about 7 microseconds. Whereas for a 20 eV neutron, we have a spread of about 3 microseconds. And this is something that's unique to this system. It's actually the opposite of what we would see through a pulsed system, which, for example, is what Ethan is looking at with the DT generator. So that's just one thing to keep in mind, is that resolution is dominated by that moderation time, and it's improved for higher energy neutrons. Now we're moving on to experiments to verify what we see through simulation. So this is a picture of our current setup. We start with the neutron source, which is the 10 microcurie MB source in this box that you can't really see here, but it's kind of here. And then we have our shielding all around. We have 20 centimeters of borated polyethylene, which shields fast neutrons. And then inside we have 1 to 2 centimeters of boron carbide sand contained within aluminum walls, which absorbs thermal neutrons and stops any kind of scattering off of the walls. Next, we have moderation. This here is our liquid scintillator detector. The neutrons coming out of the source box will hit this liquid scintillator and get moderated, and then travel along the time of flight distance. So that's detector 1, where we have our start of the time of flight window. And then finally, in this collimator here, we have our second detector, which is a lithium-6 doped GS20 glass. And this is where the time of flight ends. We're currently working on experiments right now. We have the entire setup designed and set up right now, and we have 24 hours of data with a silver target and cadmium target. However, right now we're not really seeing any of those resonance dips. So something we're working on are a few ways to either reduce our background through surrounding our detector with lead to prevent gammas from entering the detector and contributing to that background, or also using a larger liquid scintillator. Previously, we were using, it was 3 by 3 inches, and now we're using a large detector, as you can see here, which is 3 inches by 8 inches by 8 inches. And so these are things that we hope going forward will help us to better reproduce those results that we see through simulation. However, the simulation is promising. It does show that it is worth it to continue iterating on this experimental setup because this system does have very good potential to improve NRTA for a small on-site and mobile system. Thank you to the MTV because especially through workshops, we're able to really improve our work here and improve and learn a lot going forward in these experiments. Specifically, the upcoming MTV workshop on MCMP will be useful as an introduction to the code and really help with our simulations. We can do more complex simulations going forward, as well as presenting and discussing our work at MTV workshops has often led us to new ideas and improvement in the setup. So the MTV has been very important to this work. In conclusion, simulations show that this method of using an isotopic MV source for NRTA is very promising for a simpler setup and making NRTA mobile and accessible to a variety of sites. However, we do see a limited neutron flux, and we do have a limited resolution due to moderation times. Going forward, we would like to continue this experiment to just prove our concept and find ways to reproduce the background so that we can subtract that and then use higher source rates to reduce our measurement time. Thank you to the MTV, and thank you for listening.